All right, that's better. Okay, so as mentioning earlier, this is the last class of the semester. Final projects are due tonight. So make sure to get them in tonight because peer reviews need to be assigned and need to make sure everybody has enough time to watch one video and read one report and submit their peer review. So that's the reason why they're all due today. That was an extension from yesterday. And I can't extend them any further. They really got to come in tonight so that the peer reviews can be assigned so that everybody's got Friday to do a peer review. The peer reviews are technically due Sunday, but I need to make sure everyone has an opportunity to do any non-final exam work by Friday. So it's the reason why I can't extend the final projects anymore. So final projects due tonight, and then those peer reviews ultimately you can do Sunday. Other things due Sunday include mini project 8. If you want to do mini project 8, that's fine. If you don't need to do mini project 8, then I'd actually ask you not to do it. Like you can do it on your own, but if you don't need the grade, then it helps us kind of streamline the process in finals week if we have fewer mini projects to grade. And so remember that your first mini project 1, that is always counted. And then there were 7 more mini projects after that, 2 through 8. And the lowest 5 of those are automatically dropped. So you only have to do 2 of those. So if you like your 2 scores, or if you have 2 scores that you already like there, you don't need to do mini project 8. If you really want another mini project to sort of raise one of your other mini project scores up, you can do it, and that's due Sunday night as well. The other thing due Sunday night is the last muddiest point assignment. And then the only other thing that I can think of there's a concept check over this unit. So that's your final concept check that's due Sunday night. The only other thing I can think of that's kind of related to a due date is the course evaluations I think are due Friday night, Friday at 11:59. So that's optional, but if you'd like to do that, then make sure to get those in by Friday night. Okay, so are there any questions about the due dates, things moving forward? Let me turn the online chat this way so I can see it. All right, looks like we're all set. And let me turn off that toast across the top of the screen. Okay, so thanks for a fun semester. This is content that has been content that I've always thought is sort of near and dear to my heart, and it's fun to be able to have this opportunity to present it to you guys. So thanks for your patience, and I hope it was an enjoyable semester. We're going to round it out. We're going to close things up. Ultimately, what we're going to get to here is, so our ultimate goal is to introduce cellular evolutionary cellular automata, or cellular evolutionary algorithms. That is our ultimate goal for today, because you can expect to see at least some questions, at least a question mentioning CEAs on a concept check and maybe on your final exam. So that's the ultimate goal, is to build up to that. And that will also help bring Unit 8 back together with Unit 1, the cellular automata back together with the genetic algorithms, where cellular automata provide us more structure to play with when developing novel genetic algorithms. So that's where we're going with that. And so we've been talking about elementary cellular automata, or ECAs. And in elementary cellular automata, these things are named by a kind of a decimal encoding of their rules. And so, for example, so the context we have here, just as a reminder, we have a bunch of cells. that take on values 0 or 1. They have periodic boundaries, so this is sort of like a strip that wraps onto itself. And so these things take on values of 0 and 1. And so the cellular automata provides us a rule set to move from one set of states to the next. And so, this is in time. This is at time step k. And so then at time k plus 1, then the ECA rule ends up producing some output, which will be of the same dimension as the input, but will have different states. And so the way ECAs work is you look at the focal cell you're trying to update down here. In the next step, this focal cell here, this state will be determined by a function of these three states. And so what we can do is summarize basically a lookup table. So every ECA rule can be summarized by a lookup table with 8 entries. And so the ECA rule is sort of just this lookup table. And that lookup table is going to look something like, I'll put 111, 110, 101, 100. I'm going to move these over a little bit. Um, 011, 010, 001, 000. And so you can think of these as counting in binary from 0 to 8, where we've got 0 over here and 8 over here, or sorry, 7 over here. So we're counting from 0 to 7. Or we can look at this as all the previous states. And so these are previous states of these cells. So from referring to these cells here, each one of these triplets corresponds to these things down here. So if I look at these 3 cells, I say, well, when I look it up in this row, and then like 000 would correspond to this one, and 001 would correspond to this one, and so on. So if I look above my focal cell, I look at what these 3 cells are, and then I can look it up in the lookup table to see what the next cell should be. And so in that lookup table, let's say for this particular one, I am going to just do copy the previous state to the next state. Well, if I'm going to do that, then basically I just want the middle digit to pass down. So regardless of what the left and right digits are, I'm just going to copy the middle digit. So in that case, I would say this becomes a 1, this becomes a 1, this becomes a 0, a 0, a 1, a 1, a 0, and a 0. And so because I know that these are always ordered in this way, I can summarize this entire lookup table just by giving those 8 outputs, because I know that the position in the 8-bit string here corresponds to the position in the lookup table. So I don't have to actually specify the inputs, the keys. Like if this is a key value mapping, I don't have to specify the keys because the order in the list tells you what the key is. I just have to give you the values. So when I look at this here, I can say, well, what is this binary string? Well, if your familiar with hexadecimal, that makes this a little easier to do. And I can think of this as 2 hex nibbles. So these are NYBBLEs or NYBLE, I think it's BB. So a nibble is just half a byte, so it's 4 bits. And so if I look at that, I say that, well, that's 1100, that is just 12 in binary, or C in hex. I'll put maybe in brackets, C in hex. And likewise, this 1100 is also 12 in decimal, or C in hex. So if I want to figure out what this whole string is here, it's just going to be 12 times 16 plus 12, decoding the hex, which in decimal is going to be 204. And so this here is known as rule 204. And so if I go into a tool that is designed to run elementary cellular automata, then if I put in rule 204, whatever my initial condition should just be populated on down the page. So I can go ahead and try that. So if I go over into NetLogo Web, in theory, in a second here, okay, good. I'm gonna go into my NetLogo Web library here, and I'm gonna type in cellular automata, find 1D elementary, bring it up. And then under rule here, I can put 204 in for my rule. And then if I say set up random, it may be difficult to see, but up here, okay, so I guess I can't use the cursor, but so up here, when I hit set up random, it's going to be really difficult to see, but there's a bunch of green dots that were just randomly put across the first row in random positions. And if I change the density here, so like 54%, might be a little easier to see here that there's going to be more of these green dots across the top. So now if I hit go, then what I see here, if I'm going to pause it, is that rule 204 is just doing exactly what we said it would. It just copies down whatever was in the first row and brings it all the way down through here. So that shows us we know how rule 204 works. If I wanted to do something like, we'll say, what if I wanted it to toggle back and forth, back and forth? So in that case, I could say, well, I'm going to just copy this rule here to the next page and edit it. Copy. Paste. All right, so this was rule 204. If I wanted this to toggle, then I would just switch the bits here. So instead of this being 1100, I'm going to make it 0011. And instead of this being 1100, I'll make this 0011. So this nibble here is now 3. This nibble here is now 3. 3 times 16 plus 3 is equal to 51. So this here is rule 51. So if I were to go into my handy dandy NetLogo Cellular Automata engine here, and if I were to bring this down to rule 51, almost, rule 51. Now, if I said set up random, then I've got some random string across the top, and if I hit go, then I get a checkerboard. As every row in the next row swaps black and green, and the row after it, they get swapped back. So this is just showing us that that's what these rule encodings do, is that when you look at these going backwards, if somebody tells you a rule number, if you convert it into a binary string, then if you think about where the bits of that binary string fit in the ordering, you can then sort of start thinking that for the triplet that position in the order is associated with, what is this rule sort of doing? And so there are a number of rules that have kind of generalizable patterns that have been given names. So, so as an example, or let's say, so just to give a simple example of what I mean by that, let's pop up this lookup table again here. I'm going to paste in another lookup table here. And let's say that I wanted to, instead of just toggling, what if I wanted to do a left shift where any bit that was on the right just gets shifted over? Well, if I wanted to do that pattern there, then instead of focusing my attention on the middle digit, I would focus on the right digit. And then that right digit would become down here. And so that if every position in the ordering has that pattern where the right digit moves into the focal position, then this rule as a whole is going to cause everything to shift from right to left. So if I were to look at that, I could say, well, 1, 1, that already matches. This one needs to be, well, I'll just rewrite them all in a different color. So this one will be a 1 because I'm matching this digit here. This will be a 0. This will be a 1. That'll be a 0. This will be a 1. That'll be a 0, 1, 0. And so if I look at this one, and I think about, what rule is this? So I've got 1, 0, 1, 0, 1, 0, 1, 0. So if I did that, yeah, okay. So this is binary 10. So this rule together is going to be 10 times 16 plus 10 is equal to rule 170. And I can confirm that if I were to go into here and change this to rule 170, set up random, set up random, hit go, then certainly enough, it just generates these lines where it's taking whatever the previous row was and shifting it one step to the left. So it goes to show that we can, in some cases, sort of predict the complex behaviors that come out of these rules if we look across the rules for general patterns. Now, there are certain patterns that we can't predict. So if I were to look at, as an example, rule, bring this up here again, erase these. And let's say now I'm going to look at this rule where I've got 0, 1, 0, 1. And over here, 1, 0, 1, 0. So this rule is going to have a 10 over here, a 5 over here. So the rule together is going to be 5 times 16 plus 10, which is equal to rule 90. Now, if I try to figure out what's going on here, it's a little confusing. If I look, because now I have to actually think about the triplets here. So we're saying, like, in some cases, I see copying the middle digit down, like here and here, and here and here. But other cases, we see toggling going on, like this one moves it. So now I really need all 3 digits to be involved. And so when I look at this rule, it's not completely clear what pattern I'm going to get. But if I go in to simulate the thing, and I bring this to rule 90, and I'll do setup single. If I hit go with this, I get the Sierpinski triangle. So I get triangles inside triangles, and I get inside triangles. So there's a sort of fractal self-similarity. So this generates a pattern. So this very simple rule generates this, and what I mean, it is a fractal pattern in that if you zoom in on any area of the Sierpinski triangle here, you get more of exactly the same. It's self-similar. If this was a very, very large CA and we let the thing run, then I would get this giant triangle, and inside, we could keep kind of going down, and inside the giant triangle would be smaller triangles that have the exact same pattern all the way down through it. So this was an example of how very simple rules, deterministic rules, even with a single, cell here, can generate really interesting patterns that can come out of that. And it goes, farther than that. There's like another popular rule to sort of demonstrate this is rule 30. So if I were to go into here and I might get my paste up here, paste. And so for this rule, I will do 0001 and 1110. So this is just going to be 1. This will be 14. So this is 1 times 16 plus 14. That gives us rule 30. And it looks deceptively simple if the upper bit, so if the left bit is set, so if there is something on the left, then in most cases, I get nothing in the focal cell, except for this special case where if there's a bit on the left and the focal cell is 0 and the cell on the right is 0, then the focal cell gets populated. Similarly, if the left bit is not set, in most of the cases, I get 1 in the focal cell. But in a special case where all of the bits above are not set, then I get a cleared. I get, it stays clear in that. So it somehow doesn't look like anything special is going to happen with rule 30. It looks like it's going to be one of these kind of boring rules, like some of the ones before. But if I simulate rule 30, so I'll go up here and I'm just going to set up a single. So when I hit set up single, it just puts a single green dot right above here in that first row. And then if I hit go, then in rule 30, I get what starts to look boring, like a boring triangle, a little bit like the Sierpinski triangle. But then suddenly you get this spontaneous generation of these asymmetric patterns that are really weird, right? I mean, you get this, there's this triangle that shows up here that does not show up over here. And there's no obvious, like in the Sierpinski triangle, it was a clear, like an obvious fractal self-similar pattern. Here in this rule 30, it's not clear what the pattern is. I mean, there is this sort of line, there's like a ridge that's kind of going down here. But as you move farther to the right, it's hard to sort of understand the structures that are coming up here. And so rule 30 is an example of, this is an example of chaos. So this is a chaos generator. And is sometimes used as a pseudo random number generator. So you can, if you were to look at these patterns here, so chaos is great for generating pseudo random numbers because you can initialize with a seed. So I can say like set up random up top, different random seed. And then when I hit go, the patterns that I end up getting are going to, even if I change the initial conditions slightly, just by moving one green swapping the position of one green and one black dot, then I can actually get very different patterns unfolding across the rest of this. And so if you were to then take some metric of this, like the density of green at some particular row, then that can actually be a random number. And so you can actually use maybe the density of greens across these rows as like a sequence of random numbers. And so you can seed it with a different initial condition, and you'll get a very different sequence out as you have a slight change in those initial conditions. So Rule 30 appears simple, but it actually has these really chaotic dynamics, which make it kind of interesting. And last time I talked about Rule 110, which is kind of a similar beast. So if I put in Rule 110 in here, and I'm just going to do setup single, so just as a single dot up there, and I hit go, then you end up getting this kind of cool thing where it's this triangle that is just going more and more in this direction here. And what they determined about Rule 10 is that Rule 10 is Turing complete. And what that means here is what you're seeing happen here is it kind of opens up and goes to the left is a kind of a computation that is unfolding. And there are ways to take any computable function, so anything that you could write in a computer program that would be expected to eventually stop and finish a calculation, you can actually encode those in sort of a programming language of the initial row. This is going to need to be wide enough to encode all of that. So it may need to be extremely wide, but in principle, you can actually encode anything that you can write in computer code into that initial row and hit go. And the process which is taking that one bit and spreading this apart actually has the ability to do what a Turing machine does. It has the ability to look at your row as if it's a tape, move down that tape, look at instructions, and then as it needs to write into the next row, changes in state that allow things to be computed. And so it's actually possible for Rule 110 to do your computation. If you had a hardware implementation of Rule 110, you could program it to do anything that any other hardware computer could do. So that's kind of a cool thing about Rule 110. I see a question online. How will the process, so the question is, how will the process of Rule 110, how will you know when it stops? And the readout of this is not trivial, as you might imagine. Just like writing the code, writing the readout is not is trivial. But there are these tagged computational models that allow you to figure out like when the Turing machine has actually halted here. And if you look up, I think there's probably a whole Wikipedia page on Rule 110, and you can then read the details of how to actually program Rule 110 and read Rule 110. So it's a little bit outside of the scope of that. I'm not prepared to give you a definitive answer myself. I don't have to do a lot of Rule 110 programming, but it's one of these things you should know in theory you can do. And if you actually wanted to, as sort of a toy example, then you absolutely, people have written about it, and you can read the literature on Rule 110 and figure out how to actually process this out. So yeah, there's a lot of interesting rules that we can use. And the only other rule that I want to mention here is the traffic rule and the majority rule, because we already talked about them for density classification. So that's an example of combining these ECA rules together to do something useful. So in theory, Rule 110, you can program to do anything you want, but as was just asked, you got to know how to read the output. There are ways to build special purpose CAs that themselves can't do anything, but they can do one task really well. And I mentioned before that you can combine what's known as the traffic rule with the majority rule, where you let the traffic rule run for long enough for its transients to die out. And then you let take over from that the so-called majority rule. And then the majority rule will take the outputs from the traffic rule and then turn all the cells either all white or all black, depending on the initial density that you fed into the traffic rule. So it's a density classifier combining those two rules together. So let's take a look at what those two rules are to see where they get those names, just for kicks. So paste my rules back up here. All right, so the first one, the traffic rule, and this is otherwise known as Rule 184, and it takes the form of 1011, 1000. So just to confirm, 1011 gives us an 11, 1000 gives us an 8, 11 times 16 plus 8 should, if I do my math right, give us 184. So then the question would be, why is this called the traffic rule? Well, if you look at each triplet, hopefully you can start seeing a pattern here. So remember, we focus on the focal cell, like what goes into the focal cell and how it relates to the cells around it. The traffic rule is meant to represent a model of traffic flow where you can think of the ones as the positions of cars and the zeros as the position of gaps. So imagine traffic, or ones, flowing left to right. So in this direction. So now if I look at this rule, or this rule in the lookup table, then this is like gridlock. There's 3 cars in a row. And so if there are 3 cars in a row, there's no room for the middle car to move anywhere. So in the next time step, that middle car is going to continue to be there. Contrast that with the rule next to it. Here, I've got 2 cars in a line and like a convoy or whatever, but there's a gap in front. And so that's going to mean that this car is going to get to move forward. Well, if that car moves forward, the gap moves backward. So in this case, I get a 0. Similarly here, 101, it's like I've got a car that's got a gap in front of it and then a car in front of that. We don't care about the leading car because traffic is moving in this direction, but we do care that the trailing car is going to move into the gap. And that's what we see there. And so on. So here we've got a car with a bunch of space in front of it, so it'll move into that middle area. And you can do that same thing for all of these. And so in this case here, the leading car is preventing the middle car from moving, so it stays there. In these cases here, either the car moves into the gap or there's no cars coming, and so that's the reason why in the next time you end up getting gaps. So it's a traffic rule. It's simulating ones moving from one direction to the other. And one of the nice things about the traffic rule is that it itself acts as a density classifier. So this is a form of density classifier by itself, but the readout is a little weird. So the idea here is that at low density, you just get movement to the right. And I'll show you what I mean by this. And at high density, you get movement to the left. Or in other words, if we think about traffic, at low density, cars, we focus on the cars are moving from left to right. But at very high density, where it's kind of gridlock, cars have to wait on other cars. And so we really focus on the gaps moving from right to left. So in traffic, we talk about backward moving waves. And those backward moving waves are gaps that are constantly kind of moving back, sort of freeing the cars. It's like a token being passed, where the token allows the car behind the previous car to now have access to that resource. And that car moves up, and then it gives the token to the car behind it. It gives it access to the resource and so on. So in gridlock, we focus on the bubbles moving backwards, whereas in free traffic flow, we focus on the cars moving forwards. And so we see that if we go and simulate rule 184, I can do, like set up, well, if I do set up single, it's gonna be kind of boring, but let's see, 184. $188. All right, there, 184. So if I set up single and hit go, then I see that, well, setting up a single cell, that is like the epitome of low density. It's a single car. So we just see it moving. So it's doing exactly what the traffic rule said it should. Now, if I do set up random, now it's at 43% density. That's a low density situation. So if I hit go there, I see sort of a funny transient situation. So these cool transients that are happening at the top, those are cars forming convoys. So those are cars that were sort of spaced out and now get kind of clustered together into little convoys where they have to wait on each other. But then once they kind of get, spaced out just right, then these formations form and you pretty much just see lines moving from left to right. And so that's what happens at our low density. Now, if I go to high density, set up random, higher density, higher than 50%, and hit go, then now notice that the pattern has shifted its direction. It's going in the other direction. And that's being driven by the bubbles between the cars being pushed backwards as cars move forwards. So this by itself, if you were to look at this, the lines that are formed, if the line is moving in one direction, we've classified high density. If it's moving in another direction, we've classified low density. So already by itself, it's a density classifier. Now, traditional density classification in these sorts of things has a fixed point solution. And when it comes to the fixed point, we've actually done the classification and the classification's over. So we would like to turn this into something where we can read this out and in such a way that we can actually see that the computation is over, that these transients aren't continuing to die out. So that's where the majority rule comes into play. And hopefully the majority rule's name kind of suggests to you what it does. So this is majority rule. Which also goes by the name Rule 232. And so what 232 does is it's going to be a 1, 1, 1, 0, and then a 1, 0, 0, 0. So just to confirm that it is Rule 232, then this is 14, this is 8, 14 times 16 plus 8 should be equal to 232. Now, if we look at Rule 232, then what we see, I think I see a question online, what we see is that the output is based on the majority of ones in the input. So whenever there are 2 or more ones, I get a 1. So here I get a 0 because the majority is 0. Over here, I get a 1 here because there's 2 ones, but in these 3 cases, there are 2 zeros. So it's whatever the dominating bit is, that's what goes in this point, this thing here. And so if I go back to the net logo simulation, and I'm going to say, there's a switch in here to say auto continue, and I'm going to change this rule to 232. Now, if I remember how this works in net logo, it's going to complete the rule. There it goes, yeah. So it completed 184, and when it hit to the bottom, it reset, and then it started on rule 232. So the initial conditions at the top here were the final condition of 184. And what we can see here is that the high density backward moving traffic patterns coming out of 184, when put into the majority rule, turn in to a fixed point that's all green. If I instead change the density to something lower, like let's make it interesting, say 40, I don't know how confident I am in 48%, I'm gonna do 45%, and I'm going to set it back to 184, set up random, hit go. So there's my traffic rule. Because it is low density, the lines are moving in this direction. So now I can set this to 232, hit auto continue, and hit go. And now what I see is it took the initial conditions out of the 184, and the majority rule ended up, and I should have stopped it there, but there, the majority rule turned that traffic pattern into all black. So when I combine these two rules together, I get a true density classifier where it's clear what the output is. I don't have to decipher what the lines are. If it's 100% black, then that means the density was initially low. If it's 100% green, then the density was initially high. So it's a way we can combine these rules together to do computation. So what I'm hoping you see is that rules like 184 potentially could actually model real things in life, like traffic flow. And there are a bunch of cellular automata models, some that Microsoft has actually put together with some of its researchers, which model canopy patterns in the rainforest using CAs, using two-dimensional CAs, trying to understand the emergence of certain structures, multi-community dynamics and things like that. Why do you get trees of this type over here and trees of this type over here? Why do you get canopy shyness, et cetera? So you can actually model these physical systems using these CAs, or you can take these CAs and using them as computational matter where they end up having kind of a distributed mechanism for us to do some interesting computation. And I mentioned that, and again, I see the question online. I mentioned that because there are now, and I've linked to this in the module, hardware manufacturers that are producing basically hardware CAs that allow you to do things like hardware simulated annealing. Now, I don't want to go too far into this rabbit hole, but I at least want to mention that there are so-called annealing machines which are effectively hardware-based CAs that implement something called an Ising model. And this basically is a rule for updating on a lattice of binary cells. And this is a stochastic rule, which will lead me into the next topic here in just 1 second. And so I bring this up because I'm not going to go into what the Ising model is. You're welcome to look into the Ising model, but like I said, it's basically just, if you imagine a 2D CA where you have a bunch of cells that are either up or down. So they're kind of viewed as these magnetic moments, and we often talk about magnetic moments being spin up or spin down. So they've got these ups and these downs, and based on the magnetic moments around them, there's certain energy patterns. And so there are lower energy states where all of the spins are the same direction, all up or all down, or there's higher energy states where there's conflict, where one will be up and the one next to it will be down, and so on. And the Ising model has a temperature element to it. And so at high temperatures, it can basically reach any state. You can actually get ups and downs kind of next to each other. At lower temperatures, if you're already at low energy states, then it's very difficult to get into those high temperature states where everybody's different. So there's actually a way to anneal an Ising machine where you can take it and it's sort of frozen in sort of a frustrated state. Well, I don't want to say frustrated. It's frozen in a state where you've got ups and downs that are kind of randomly haphazard around. If you increase the temperature, it allows those states to start flipping. And then if you slowly decrease the temperature, then it allows those states to settle in to sort of a purer thing where they all kind of agree. And then there's sort of relationships to saying, how do you make a permanent magnet? So permanent magnet is kind of a similar thing where you can heat a bunch of iron up, you can put a magnetic field through it, you can cool it down while a magnetic field's present, and then it'll hold on to those states. And that's how you get a permanent magnet, where all of these domains are kind of in, they're synchronized together, they're locked together. So a reason I'm bringing this up is there are ways to basically program the energy function as in simulated annealing. And what this means is that this is a hardware platform. It's very, very fast that can solve simulated annealing problems. So how did they build the hardware platform? The hardware platform was effectively a distributed substrate for doing distributed computations. It was just a hardware implementation of a cellular automaton. It's easy to implement an Ising model as a CA. So you can build a hardware version of an Ising model. But once you have an Ising model, it's easy to translate an Ising model into simulated annealing. So the ability to build a hardware Ising model allows you to build a hardware annealing machine and then get really fast simulated annealing, where the annealing is actually going on a hardware chip. So I just want to mention that that's one of the applications, that more realistic applications of how you can use CAs to build novel hardware. All right, so I see, I think, a question online. So the comment was, let's see 50% density for the traffic rule. And I leave that as an exercise for you. You're welcome to go to netlogoweb.org, and you can definitely check out Rule 184 for density 50% and reason about what you get for that case. I recommend running it multiple times. So generating a new row with 50% multiple times, and think about that. Okay, so that allows me to transition briefly to mention to you stochastic cellular automata. So remember, I think my goals for this, if I go back to my title here, is that my goal is to bring you to refresh ECAs, introduce stochastic CAs, and then briefly talk about CEAs. This is kind of the ultimate goal here. And I think we can do that. And this will be the last thing that I will bother you with this semester in terms of new content here. So, so this annealing machines allows me to think about, or to introduce, stochastic cellular automata. And in stochastic cellular automata, the transition rules are probabilistic. And so there are lots of different, I mean, we've actually, like, so the Ising model, that would be an example of that. If you actually look into how the Ising model is implemented as a CA, the transition rules from one step to another are probabilistic. And what I mean by that is, so there's elementary stochastic, so there's the stochastic version of ECAs makes this, I think, a little easier to understand. And the idea here behind the stochastic version of ECAs is you can think about each rule. Remember, each rule is a triple. And if you think in terms of, like, superposition, for every triple I get, let's say my triple is 1, 1, 1, I could output a 1 or I could output a 0. Now, in the deterministic elementary CA, you just choose one of these. You say, is it a 1 or is it a 0? In a stochastic CA, you choose a probability. So like P and 1 minus P. So this is saying that when the previous 3 bits are 1, 1, 1, then in that case, we flip a coin weighted so that we get a one output, a heads from that coin with this probability. So now we, instead of summarizing an elementary CA with a string of 8 bits, 1 or 0, we summarize a stochastic CA with a string of 8 probabilities. And each one of those probabilities correspond to the probability that you'll get a 1 in that particular case. So they're conditional probabilities. So this is the conditional probability of a 1 when previous state is 1, 1, 1. So if you like, probability of a 1 given that previous is 1, 1, 1. All right, so, and if I go into NetLogo Web, for example, I can go into the cellular automata. And I should find in here CA stochastic. And it's going to take a second to load here. And then now we can see in CA stochastic, I don't have this nice rule 150 whatever, but I have this grid of probabilities, of 8 probabilities here. And so they have examples. So they say, you know, I'll set up example 2. And if I do that, it sets up this example where it's 0, 0, 50, 50, 50, 50, 100, 100. I guess I should read those. I've never liked how they've ordered these. So they're doing like 0, 1, 2, 3. So the most significant bit here, I have to read this way. So it's like 0, 50, 0, 50, 50, 100, 50, 100. So if I do that example, and then it set up some initial conditions there, now if I hit go, then I get this cool pattern. It's kind of a maze that's coming down through here. So what's I think is neat about stochastic CAs is when you hear them being stochastic, it kind of sounds like the output should be fuzzy. Like it should maybe look like a Sierpinski triangle, but like it's going to be noisy or something like that. But that's not always what actually happens here. So in stochastic CAs, you can get these highly apparently structured patterns, but it's like there's just these minor asymmetries that pop up here. So this, you know, you get these like maze-like structures out of this thing where they don't always do exactly the same thing because of the probability, but it's not just like a fuzzy elementary CA. So these can be sort of fundamentally different because deterministic CAs are so chaotic, implying that a small change in initial conditions can give you very different patterns. If you combine that with probability, then you get a whole bunch of really cool patterns that can come out of that. So I won't spend a lot of time on this. I'll just go to some other random example, set up example, hit go. And so here's one that is a little bit more like the noisy Sierpinski triangle example here, where you get some sort of development of complexity and then it dies out. So there's kind of an interesting transient. These sort of look triangular, but they're not quite triangular, and then they fall away. So stochastic CAs give you a bunch more richness. They can represent a lot more phenomena, which kind of makes them cool. So that's stochastic CAs. While I've got this up, are there any questions about stochastic CAs or any of the elementary CA stuff? It's mainly just a survey of this literature. Again, CAs are often used in modeling, but they can be substrates for computation as well. I mentioned last time, but I forgot the model, that in deterministic CAs, there are reversible CAs. And I thought that NetLogo came pre-built with one, but I couldn't remember the name that they used for it. And so their name was Vance, virtual ants. And I just want to bring this up. This kind of refers to next time. Or last time. This is a very simple CA where I can choose the number of Vance, virtual ants, Vance. If I hit setup, then it puts a bunch of ants in the center, but they have random orientations. And then I can hit forward. And what we've got here is each one of these ants is following a deterministic rule to choose its next step. And you might think that a single agent following a deterministic rule, that the rule is based on its sort of like its orientation and what the color of the cell is underneath it. And they summarize those rules. If I pause this here, if I just scroll down here and go to model info, they summarize the rules for this particular case. And they say that the rule is, I'm looking at this, how it works here. These vants follow simple rules. Each faces north, south, east, or west. At each time step, they move to the next patch. It looks at the patch. If the patch is white, the vant colors it black and turns to the right. If it's black, it colors it white and turns to the left. Doesn't sound that sophisticated. But if I run this rule forward, I end up getting these sort of interesting patterns that come out of here. And that may be kind of interesting that it does seem to grow and it starts painting the space. But what's cool about this to me is that I can actually run that rule in reverse. And when I run that rule in reverse, it actually rewinds the system. It undoes all the damages here. So in other words, there's actually no entropy generation here. There's no loss of information. This is a reversible CA, which means that if I let this thing run, I would get this very complex pattern, and I might think that that pattern gives me no information about the initial condition. But because I can run the rule in reverse and get the initial condition back, that means no information was ever lost. So there's something kind of cool about that we have these reversible phenomena. So if I let this thing run to its conclusion here, they all come back to the center, and then they kind of restart the pattern because it's reversible. And so it's as if the universe came into a point and then expanded again. It's like this was like an hourglass shape where it kind of came into a bow tie in between that. So anyways, reversible CAs are a thing as well. You can prove that these vants are reversible, meaning that you can run them forward and backward and get the exact same trajectories. The rules apply in both ways. There's no loss of information. Okay, so that's that. All right, so at this point, I want to take the last few minutes to connect these CAs back to Unit 1 on our evolutionary algorithms. So are there any questions at this point about the stochastic CAs, evolutionary, or the elementary CAs, anything else CA related? Make sure, I think that's the same comment as before. Yeah. All right, great. So that's the last model that I'll run there. Last net logo you'll see for me. So, so this brings up the topic, the closing topic here of cellular evolutionary automata. So these are, I guess I'll say decentralized, I guess I can mention that, cellular evolutionary algorithms, or CEA. I think a lot of times the C is lowercase when people write these. All right, so what are these and how do they differ from normal GAs? So a normal GA, so a simple EA that we work with, the ones we've seen so far, well, except for maybe the distributed GAs, it starts getting into this a little bit. Simple EAs are panmictic. So what I mean by panmictic, so mictic is kind of like mixing, and pan is sort of everywhere. And so that means that any individual can mate with any other. Sure, there are fitness consequences that may prevent certain individuals from mating. They may not get into the breeding pool, but there's no spatial relationship in mating. Now, again, you could talk in distributed GAs, things got a little bit different. is in multi-objective sort of things that, there might have been niching that prevented some interactions, but broadly speaking, the basic idea of it all is that space wasn't really a part of the GA. So, in cellular evolutionary algorithms, you actually make the population structure even more rigid than we saw in distributed GAs. So we're actually going to alter the neighborhood structure of a GA according to a CA. So we're going to use a cellular automaton as a rule for who gets to compete for the next spot. So the idea here is, in sort of the simplest example of this, imagine a population of individuals on a ECA-like line. So then we've got, individual A is next to individual B, is next to individual C, is next to individual D, and so on. And so they all sort of have their own spot in space. And so that will eventually end here. So this is our GA population. And this is generation K. Well, so then the question is, who inherits these spots? Who gets to go into those spots in generation K plus 1? And so what we can do is actually use a cellular automaton to describe the neighborhoods. So we can say, and I say it's like using a CA, but it's almost like really what's happening here is that the update rules, all I'm really defining is the neighborhood on which the GA acts. And it's almost like the GA is the CA's update rule. That's kind of a better description of it. So I can sort of say that maybe my neighborhood here, I'll use the highlighter, my neighborhood is similar to an ECA, where these three individuals determine the fate of this central spot here. So then this is sort of think of this as a 3 individual GA competing for the central spot in next generation. So for an ECA, type neighborhood, you just, like I said, it'd be like a 3 individual, but we could imagine this also being expanded to multiple dimensions. And so you could actually put not just all the individuals on a line, but you can put them into a grid. And you would define neighborhoods. And so again, you would use, so what I mean by this GA, that would mean that among this little area here, then you would have one winner after you went through the process of selection, recombination, and mutation. So it like puts them through this bottleneck here. But that also means that these 3 individuals get multiple shots to get into the next generation. So it's not like a really strong bottleneck, because A, B, and C are all going to compete for this middle spot that B is in. B, C, and D compete for the spot that C is in. C, D, and E compete for the spot that D is in, and so on. So each individual gets multiple shots at getting into the next generation. But the competition for each spot is pretty fierce, right? It's a small number of individuals, a small number of spots. But like I said, you can expand this to the 2D case, so you can have multi-dimensionals here. So where we could have, a grid of nine cells all competing for this focal cell. So this is 9 individuals in subpopulation competing for central spot. And so it's like the GA operators are the CA update rules. All right, so why are we doing this? Is it just purely sadistic or masochistic, I guess? Or what does this get us? So what's interesting about this is it allows for new ways to play with basically exploration and exploitation. So these neighborhoods can actually change during the operation of the CA. So as an example, I could have, for a certain set of generations, I might have a grid that is such that there's some focal cell here, and above it, it's got its north neighbor, its east, its south, and its west neighbor. And this runs for a few generations. And then after that, then I get a reshaping of the space that's sort of like, imagine plate tectonics or something like that. And what ends up happening is instead of getting, let's say, a 6x6 grid, which gives us, 36 cells, instead this gets shifted into a 3x12 grid, which is the same 36 cells. But now the topology is such that the whole thing is this giant rectangle. And in this giant rectangle, the north and south neighbor might be over here, but the west and focal and east neighbor might be over here. And so this was like a restructuring population during runtime. And I'm not going to really say much more about that because we're right here at time. But the idea here is that if I play around with how sort of dispersed these individuals can get relative to the whole grid, then I can actually play around with selective pressure. So there's sort of there's ways in which the kind of sphere of influence of each individual sort of relates to this kind of selective pressure in this way. And again, I don't really have time to go into it as much as maybe I'd like to here, but the big takeaway here is that by tuning space, I can actually tune parameters that in a GA were numerical parameters before. So this just gives us a different type of knob. So in our old GA, we might have to change the selection operator and all of its hyperparameters, and that's how we would change selection pressure. And if we wanted to do that in an adaptive way, we have to come up with some numerical update rule for those hyperparameters. But here, the hyperparameters actually become physically embodied. You can actually change the structure of the neighborhoods as they go over time. You can dislocate individuals, you can put them all back together, and so on. And the physical changes to the space map to very similar changes to those numerical changes that you make to the hyperparameters. And that's kind of the thing that CEAs give us, is a way to sort of embody physically the notion of certain hyperparameters. And maybe that's good for you if you're doing some sort of evolutionary robotics thing where, you'd rather not broadcast a bunch of parameters to a bunch of robots. You'd rather just like their spots in space determine those things. Maybe they can self-organize so that if they all cluster together in a particular way, they're going to be more exploration-based. But if they all separate apart, they'll be more exploitation-based, and so on and so forth. So it provides for more degrees of freedom for these design challenges. But that's it. I'm already over a little bit over time. This is all that we've got for the class here. I just wanted to make sure we introduce the CEAs. A bunch of due dates on Sunday. The course evaluations due Friday night, and I guess that's about it. So if you've got any questions about there's a final exam, a sample, a practice exam that's online. You can feel free to take that. A lot of it will disappear Sunday night, and so make sure you kind of play with the practice exam before Sunday. But otherwise, the final exam's open notes, open book. And that's all I got. So if you have any other questions, feel free to send me notes. I'll hang around for anybody who's got questions online. Otherwise, have a good summer, and we'll see you around.
Professor.
Thanks all. Any